Hello, everybody. I hope that you are watching this video after you just watched the new liquid nitrogen demo that me and my friend Andrew led. Hopefully you enjoyed watching us freeze things and then smash them, which is always super fun. It's one of my favorite parts about material science. And I just also wanted to give an introduction in case you don't know me. My name is Abby Carbone. I am, I guess now a second year, which is crazy, second year graduate student at Stanford University studying material science and engineering. And if you don't know what that is perfectly okay too. Go ahead and check out any of my other videos where I go into a lot more about chemistry and physics and material science and engineering and all sorts of stuff. So if you are curious to learn more about science, definitely check those out. I wanted to take a minute to just kind of briefly go over the applications of these demos because, the scientist in me thinks, wow, this was awesome. I love learning about the fundamental material science. I love learning about how atoms move and how they can change and, the inner workings of the universe or whatever. But the engineer in me wants to know, okay, this is cool, but what's the application? Why do we care about this? And it turns out that this idea of things changing their behavior, especially mechanical behavior, as we change their environment has serious implications for material science and, for how we operate in our everyday lives. And so the first example that I usually think of is actually the Titanic. And I want you to take a second and think about why our previous videos about freezing something and then smashing them and then breaking them, how could those experiments give us any idea of why the Titanic sunk? So I'm just gonna do one of these because I want you to actually think about it. But there's no quiz at the end, so I guess we'll just move on. Okay, thinking about the problem first. We know that the Titanic was an absolute feat of engineering. This thing was the biggest, grandest, most amazing ship that had ever graced the ocean waters at this time period. So it doesn't really make a whole lot of sense that when it hit an iceberg, this giant feat of engineering, to hit a dinky little iceberg and then just crack and break and sink, right? That doesn't really make a whole lot of sense, but it does if you think about it from the perspective of the demonstrations that we did. So the first thing that we know is that it was sailing and it hit an iceberg. We know that if there was an iceberg in the water, that means the water was probably very cold. And it turns out, if we take the same metal that the Titanic was made of, and we put it in that very cold environment, a very similar thing happens to the metal that the Titanic was made of that happened to the new penny after we froze it. The fundamental materials properties changed of the Titanic once it was in those cold ocean waters. I just want to say, if I have any engineers in the audience or any scientists who work with metals at all, it's not exactly the same as far as what is happening fundamentally kind of on an atomic level. Those mechanisms are slightly different, but the end result is the same. So we're just not going to worry about that in case anyone was going to call me out on that. So when the engineers were doing all of these materials tests on the Titanic before it, went off on its maiden voyage, they were doing it all in warmer ocean waters, which means that the materials failed ductily. So you would hit it and it bends. But when they put the Titanic into those cold ocean waters, when the boat hit the iceberg, it didn't bend when it hit it. It fractured. It fractured in a brittle way like a ceramic. Similarly to our penny, when we smashed it initially at room temperature, it bent, right? But then when we smashed it at liquid nitrogen temperatures, it just completely shattered. So the similar thing happened to the Titanic. And in fact, if you know anything or even remember the Challenger explosion, a very similar thing happened there as well, where the O-rings that were used, it was too cold before the day of the flight, and the O-rings that were used underwent something similar to our racquetball, where the O-rings would actually crack a little bit. And if you are familiar with any sort of vacuum system, the O-rings are a crucial component to sealing away different things that shouldn't be in contact. And so when those O-rings broke, that meant that things that should not be mixing together were mixing together, and that kind of caused a whole chain reaction and unfortunately ended in the Challenger explosion. So This is something that, materials engineers have to think about every day when they're designing new parts for new things, when they're choosing, should I use this kind of metal versus this kind of metal, or maybe even a plastic or ceramic or whatever. These are just things that we have to keep in mind every day. And these experiments, while they're obviously awesome, again, smashing things, like what more could you want out of a science experiment? While they're awesome, it really does have real world applications and consequences. And I don't know, I just think that was really cool. So I just wanted to share that with you all. And hopefully I will see you all soon, grad school permitting. Hope you all have a wonderful rest of your morning, day, or night, or whatever time it is that you're watching this video. I don't know what else to say, so I'm just gonna, okay, great, go science. Okay, bye. I don't know if y'all have talked to a camera screen, like by yourself in an office. It makes you feel like a literal crazy person. I was like really hoping that no one was gonna be like walking by these windows, just seeing this crazy person just talking to themselves at a camera to no one in particular.